Welcome to our projectile motion physics vlog. Buckle your seatbelts because you're in for a ride that just looks like projectile motion itself. Okay, so this is our first draft. It consists of a tube that's fixed on a piece of wood, and that wood has a hole in the middle, and on it there would be a nut that is fixed onto the tube, and that's how you're able to change the height of the tube. And then on the bottom of that piece of wood there is another screw there, or a bolt, that is attached to the base, and that would allow for you to change your DX because it can move back and forth. Okay, so that first draft we made, yeah, we all decided that it was really complicated and we weren't able to build something like that. We didn't have the money to buy all the materials, and the chances of messing up would be super high, so we just decided not to go with that idea. So this is our second draft, which is a lot simpler than our first one. So we would have a wire that would be on something like a piece of cardboard or a piece of wood, and that would be the path that the marble or ball bearing would follow on. And in order to change the DX, we would have something like a hinge attached to the end of it, which would change the angle, and then the DY would be affected by where we drop the ball on the metal wire. So before we actually build the entire thing, our group decided that we should make a prototype and see if we're able to build a structure like this. So our prototype materials will be the cardboard as the base and the wire itself, of course.
I'm just setting this down real quick to figure out how it's gonna work. So it's smoother. We have something to put the wire on.
We have scrapped our idea on using metal wire because we're not strong enough to bend metal. We have resorted to rubber tubes.
This was my idea, Dylan.
Which was garbage idea.
Oh, now it's working.
So while we were trying to bend the wire to fit its ideal J shape, we realized that we couldn't bend the wire perfectly, and because we couldn't do that, the path wouldn't be perfect. So as the ball would roll down, it would not roll properly and it would slow down or increase in speed, which is not good because if it's not consistent, then we won't have consistent landings for the real thing. In addition to that, we didn't know how to attach it onto our mechanism itself, since wire is so thin and our cardboard was a certain width as well. Our group could not find a way for the wire to stay sturdy onto the cardboard, so we decided to change our idea and use tube instead. For a visual effect on what happened when we tried to bend wire, so we tried to bend wire, and as you can see, the surface of the wire would not be straight. There would be a whole bunch of lumps and bumps in between. So when we tried to roll our marble down, so I'm just going to draw a marble right here. So as we tried to roll the marble down, the marble would not fall straight and it would just bounce and jump around. And for a visual effect, so now to fix that problem, we decided to use the rubber tube. Once again, we thought that the tube would be a better option because it is easier because it already has that circular shape. there would be no bending required because rubber tube is very flexible, and it would be easier to attach onto the mechanism if we just, since it's a lot bigger, so our entire scale must be bigger as well.
Yeah, so this was a bust. David picked out a tube that was like pretty much pure. We collectively sticky. I just listened to it.
Okay, we ran into a problem. So we didn't take into the consideration the width of the tube, so it was too small, so we tried to cut it open. But because it already came in a package where it was already bent, when we cut it open, the edges kept on bending in, so the ball wouldn't roll down because the edges kept on pressing against the ball. We couldn't find a way to bend it back into its original form, so we decided to give up on that idea. So to give you another visual, so here's the rubber tube that we decided to cut open, and as you can see, it's not straight because it was already rolled in a circle, so it was bent, right? And because it was bent, the sides of the tubes kept bending inward, and so if we were lucky, the ball would even start rolling, but it would still stop because the width was too small. So to Okay, so we have to fix that problem now, right? So Dylan suggested that we would go back to wire, but instead of using the aluminum wire, we would use something more malleable, for example, like copper. Since it's more malleable, it'd be easier to bend, and we would hope that it'd be easier to make it straight. And we've also found a way to make it straight using a drill and materials that we have around the house.
No, because you have to. The thing is, when you have it, you want it to go as far as you can, and when it goes up, you want.
So we decide on copper wire.
Do we decide how? David, if you want to get it, get it.
So at Home Depot, David found a piece of tubing, and he thought that would be a really good idea for our projectile motion project, since it's like sturdier than the rubber tube and it can also bend, so it's pretty flexible. So we decided that if the copper wire doesn't work, that we would also go with his idea for the tube.
So if I have it connected, so say the table is like the wire. No bounce. Yeah, see? It's not that bad. Like, we can work it.
So after David's explanation of how he wanted to use tube, we decided to use both the wire and the tube. So as a visual, we would have our tube that would eventually be cut open so that it'd be open-ended. So we would have the ball roll down on the tube for most part of it. Since the tube is sturdy and it can retain its shape, that'd be good for the ball. But after, at the end, we would attach the copper wire so that it'd be extended, so the ball would have more path to travel on, which would eventually, hopefully, go into our target.
Dude, that's perfect. That's actually so good.
So after all that hard work and struggle, here's a picture of what our model looks like. They're so proud, look at how happy they are.
You can't use the wire anymore because it's too twisty. So we decided to use this instead.
Which barely makes it.
Barely.
Okay, so our copper wire idea didn't work as well, so as we tried to twist the wire using the drill, it became even more twisted because the way that you straighten it is to basically twist it so much that it becomes straight. So then the surface would become really bumpy, and that's not a good surface for a ball to roll down. So here's a short video clip on how we straightened our wire. So you can see that they have a drill attached to a clamp and that they're basically twisting the wire over and over and over again. But what we didn't realize is that the wire just kept on twisting and twisting and twisting until it became straight, but it didn't actually become straight. It's because it's been tightened due to the twisting that it became straight. So yeah, that didn't work, and so instead we just decided to cut open the tube and use it by itself instead.
We're so productive.
Yeah, that should be okay. Once it's 1 meter's up here, this should be 90, this should be 80.
So here is a picture of our structure. As you can see here, this part of the structure is what we use to change the angle, so that can change the dx. And that angle is sustained by these strings that are attached to nails up here. And then how we change dy is by dropping the ball in different places on the tube. So here is our calibration data. We have our dx, our dy, and centimeters, and then we have the angle for where we drop it at. So there's 75 degrees, 60 degrees, and 50 degrees. And then we have these numbers that tells us where to drop it. So we would have tick marks going from 100 and descending by 5s all the way down to 5. And just to clarify, these tick marks do not correspond to the actual height of where we're dropping it. They're friendly numbers to tell us where we drop it in relation to the tube. So to give you real numbers, tick mark 100 would be 57.7 centimeters, and tick mark 60 would be 41 centimeters, and tick mark 30 would be equal to 31 centimeters. So now we have to find two sample solutions and finding their launching speed. One of the examples that we will use is the dx will be 100 and the dy will be 10.
100 distance, 10 height.
So we know that Vx equals Vi cos theta, but we can also find Vx by dx over t. We have a timer on how to get t.
100 distance, 10 height.
So we measured our dx and it was 146 centimeters, and from our timer it was 1.06 seconds, so we can plug those in and we get vx is equal to 137.74 centimeters per second. So using our vx we can plug that in into the other formula, and with our angle cos 60, and now we have solved the launching speed, which is 275.48 centimeters per second or 2.75 meters per second.
Little guy. This is little guy, right? That's 10, so this is little guy.
20 centimeter, 20 distance, 10 height.
Hold on. Are you?
Now we can do the same thing but with different dx's and dy's. So this one is 20 centimeters distance and 10 centimeters height. So using the same process we can find dx and t once again with our timer, and we solve for our vx to be 61.29, and then we sub that back into the other equation and we solve for vi, which is 122.58 centimeters per second or 1.23 meters per second. Alright, conclusion time. So we made all 5 runs for our test, which was really good. So we've gone a long way. We've come a long way from this project. We've realized a lot of our flaws and we were able to fix that, which was good. We've done a lot of work in the past couple of weeks. Maybe we've been stuck in Dylan's basement for longer than we should be. Perhaps one of us have gone insane, but a soul for a soul, you know? Alright, thanks for watching guys. See you later.